I'm Greg Skidmore, the Director of Propagation Software Tools at REMCOM, and today I'm going to walk through a demonstration of ways to simulate 5G, mmWave, and FD-MIMO. The objectives of our webinar are to use Wireless InSite MIMO to predict performance of 5G mmWave FD-MIMO systems in urban small cells. Our simulations will apply beamforming for multi-user MIMO and predict signal to interference plus noise ratios and throughput for various scenarios. And we'll discuss real-world challenges for systems and ways that simulations can help. We expect this webinar to last approximately 40 minutes plus questions and answers at the end. At any time during the webinar, you can ask questions by entering them into the dialog panel as shown on the screen. You can optionally undock this panel and stretch it out to make it easier to add your questions. So mmWave provides many opportunities in 5G. One of the most significant is the new spectrum that it adds. But in addition, large arrays for things such as FD-MIMO can fit into a very small footprint. And so this makes it a very good opportunity to be able to implement massive MIMO and FD-MIMO for 5G and to use techniques such as multi-user beamforming, which can provide high gains and also increase spectral efficiency. But these new technologies do come with many challenges. mmWaves suffer high path loss and large penetration losses from structures and foliage, and there is also more complex scattering that impacts the polarization and the phase of signals. In addition, the increased use of MIMO and FD-MIMO in recent versions of 4G and also 5G make channel modeling increasingly complex. So these challenges bring significant complexity for planning as well, and predictive simulation tools need to advance to help. Some of the specific opportunities for mmWave and 5G are outlined in the 3GPP report shown on the screen. This report outlines 3 general use cases for 5G and 12 deployment scenarios shown to the right. 5 of the deployment scenarios allow for mmWave options. 3 of these are traditional, including indoor hotspots, dense urban environments, and urban macro environments. And there are also some new ones such as high-speed trains and satellite extensions to terrestrial propagation. The focus of this talk is on predictive simulation for enhanced mobile broadband in dense urban scenarios. Some of the main effects that mmWave propagation suffer begin with propagation loss. So path loss at 30 gigahertz suffers about 15 to 30 dB more loss than at the traditional bands below 6 gigahertz. In the plot to the right, we see on the blue line 1 gigahertz to 10 gigahertz in green, and we see 30 gigahertz in red, and can see that the losses are much more significant at the higher frequencies. Atmospheric absorption also has some significant attenuations, particularly at certain bands around 22 and 60 gigahertz, but also the higher frequencies in general. These are often expressed in terms of dB of loss per kilometer, and it happens that at 28 gigahertz, the dB loss per kilometer is only about 0.13 dB per kilometer. And so this isn't too severe as long as the ranges are not too long. Rain attenuation can also be significant, but like the atmospheric absorption, the losses are not too strong at lower ranges. So all of these heavy losses tend to make mmWave best suited for small cells and indoor applications where the distances traveled won't be very large. mmWave also suffers from penetration losses from structures and trees. Starting on the left, we have a plot of penetration losses that might be typical for 1, 2, or 5 trees, shown in blue, green, and red respectively. And you can see as you go up from 1 gigahertz to 10 gigahertz and above that the trend is very strongly upward. And large numbers of trees, you can see losses of 10 or 15 dB beyond what you would expect at the lower frequencies. Penetration losses are also very high. Traditional older building structures, as defined by 3GPP, might be expected to have approximately 30% windows, and the windows in older structures tend to be fairly transparent. So we see glass attenuation in green, and while that increases, it's not too strong even at the mmWave frequencies. And so 3GPP has a curve defined shown in magenta for older buildings that has an upward trend and might see perhaps 10 dB more loss. But of greater concern is probably the fact that new buildings are being constructed with infrared reflective glass. We show the loss from this in red following the 3GPP model, and the loss for concrete walls is shown in gray. The concrete attenuation goes up dramatically, but when you combine both concrete loss and the IRR glass losses, when you get up to the millimeter wave frequency bands, you see losses well above 30 dB. This is much more significant than we had at the lower frequency bands. However, reflections actually look very similar. There are many resonances depending on wall thickness and specifics of materials where there can be spikes of loss at different frequency bands. But in general, when you compare concrete, glass, and wood, as shown on the plot to the right, you'll see that the reflections are very similar at millimeter waves to what they are down at the lower frequencies. And so there are many aspects then of outdoor propagation and multipath and reflections in an urban environment that really are quite similar to what they are at the lower frequencies. One important distinction, however, is that diffractions around corners drops off very rapidly when we go up to millimeter wave frequencies, and so reflections and scattering become a more important effect for propagation. Another key effect is diffuse scattering. This has received a lot more interest as frequency bands have gone higher. And part of the reason is that surfaces that in the past would have been considered fairly smooth and flat actually may have variations such as mortar joints and other architectural features that end up being fairly large compared to a wavelength. The result of this is diffuse scattering, and this causes signals to lose their coherence and their polarization, and also to scatter in many more directions. The plot on the left shows a couple of different scattering models, one that allows scattering to spread out the reflection directions in the forward direction, and one that also includes some backscatter terms. So the Wireless InSite model that we'll talk about today has implemented a scattering model that includes these kinds of effects. Next, we have full dimension MIMO. This has received a lot of attention in the literature preparing for 5G. And what full dimension MIMO is the use of tens to hundreds of base station antennas arranged to direct beams in 3 dimensions. The antennas that are arranged in arrays that are both vertical and horizontal, and this gives them the ability to direct beams in different directions, including vertical and horizontal directions, as shown in the figure on the right. The goal with FD-MIMO is to be able to direct beams to several UEs at the same time in the same frequency band. The use of the tight beams can allow an FD-MIMO system to increase the gain and thereby the signal interference plus noise to each of the UEs. But the fact that it's generating these beams in the same frequency band simultaneously also allows it to increase its spectral efficiency dramatically by transmitting to perhaps 8 or 10 UEs at the same time. When we talk about this in combination with millimeter wave, one of the great advantages is that an array is typically spread out with the antennas on the order of a half a wavelength. And at higher frequencies, millimeter waves such as 30 gigahertz, half a wavelength is only about a half a centimeter. And so you can create what would be considered to be a very large array in a very small footprint that could even fit on top of a lamppost or in another type of small cell configuration. This makes millimeter wave well suited for FD-MIMO. Another technology that comes into play as we consider MIMO technologies is coordinated multipoint. There are 3 general categories of coordinated multipoint. The first is coordinated scheduling and coordinated beamforming, shown to the top right. This is simply ensuring that the base stations share enough channel state information so that they can ensure that only one base station is forming a beam to a device at a time. That way they don't end up interfering with, by both forming different beams at the same time that interfere with each other. A second type is joint transmission. In this case, base stations share not only channel state information, but also the data that needs to be transmitted. And from this, they can combine their beams and form a stronger beam to a device. This is particularly useful when the device is along the cell edges, where this can increase the signal to interference plus noise and increase the throughput. And a third type is a special case of joint transmission called transmission point selection. In this case, the base stations share channel state and data, and that allows them to make decisions to dynamically choose which base station should be transmitting at any point in time. So an important question is how we can capture all of these effects in simulations for planning and prediction. 3D ray tracing has been used for years to assess systems in situ in complex environments such as urban environments, and it's increasingly being used for planning in complex urban scenes. Ray tracing can provide accurate channel data, including the times of arrival, angle, phase, and polarization. In our example shown to the right, we see the top 25 paths for propagation between a base station and a UE that's traveling along a route through an urban area. These paths have both phase, polarization, and time of arrival, and they can be plotted in terms of what is called a complex impulse response, shown in the plot to the right, where we can see copies of the signal as they arrive and calculate important metrics such as the RMS delay spread. These different factors are also very important for MIMO technologies, and so a ray tracer becomes a good tool that can be used to assess the performance of MIMO. Some of the challenges in using a complex full three-dimensional ray tracer are shown below. This includes runtime. The simulations in our presentation today use Wireless InSite's GPU accelerated ray tracer along with MIMO optimizations to minimize how much additional runtime is required in order to simulate large arrays on MIMO antennas. Another typical challenge is the data. Data these days for buildings, foliage, and terrain can be obtained from data providers, and the price has been coming down over the years. So obtaining data to set up a complex scene, such as the figure shown to the right, is not as difficult as it once was, and REMCOM has partners and can help with users to find data and set up their problems. The third is the complexity of 5G. Just thinking of the different things that we presented in the previous slides, we can see that 5G is getting increasingly more complex in terms of what's required to model the different things that are going on in a simulation. And REMCOM is focused on continuously developing new capabilities to be able to handle these new complexities. So we prepared an example for this webinar that predicts the performance of mmWave FD-MIMO systems in a downtown area in Boston. This demo has 3 base stations, 2 placed on lampposts at about a 15-meter height, and 1 placed about 45 meters up on the side of a building in order to allow it to propagate over trees that are present in one of the squares in downtown Boston. The frequency was 28 gigahertz, and the bandwidth was set to 100 megahertz, which is the component carrier bandwidth expected for 5G according to a couple of the standards listed here. We then defined 2 cases, one with a large FD-MIMO array. Our array was an 8x8 array of patch antennas set at plus and minus 45-degree cross-polarized angles. And for comparison, we also included a case using a baseline of 120-degree sector horns so that we could compare how much improvement we get by going from one antenna to a large array in a MIMO configuration. For both cases, we use an output power of 5 watts, resulting in a total overall max EIRP from the array in a focused beam of potentially up to 66 dBm. And we had a total of 128 total antenna elements from this configuration. The receivers in this example were simple dipole antennas at a number of different UE positions. Next, we constructed a table to estimate throughput as a function of signal to interference plus noise ratio. We looked at several different references, extracted data for approximately 1% block error rate, and constructed a curve, did a curve fit using a fraction of the Shannon theoretical capacity, and found that approximately 45% of Shannon capacity fit fairly well to the data from these 3 references. This caps out at the highest possible throughput from the 3GPP specs at around just under 100 megabits per second for a 20 megahertz band. This was all based on the LTEA specs, allowing up to 256 QAM for a 20 megahertz band. So to scale this up to 100 megahertz bandwidth for 5G, we simply applied a factor of 5 times this curve and used these curves for our throughput lookups for the simulations. We began with our baseline case using 3 sector horns and our UEs, and we generated simulations for a field grid throughout the 3 cells that we set up. In this case, for noise, we used an ambient noise of negative 167 dBm per hertz, and we included interference between the base stations and each other to account for adjacent cell interference. The SINR map shows good coverage, particularly near the line of sight of these different base stations. But as we look at the colors going from good coverage in the reds and oranges down to very poor coverage down in the blues, we can see that there are definitely some areas in some of the side streets and other non-line of sight areas and along the boundaries where the cells are interfering, where the coverage is not as good. In blue, we have circled some of the areas where there is shadowing from buildings and foliage, and in red we show some of the areas where there's interference between cells. Next, we calculated the throughput using our constructed throughput curve and allowing up to 256 QAM for the 100 megahertz bandwidth. The results are shown in the plot to the right again. And we can see that in the line of sight areas or close to line of sight, we see some very high throughputs up to about 500 megabits per second. And in the other areas where we noted the lower signal interference plus noise, there are definitely some large regions with dropouts. So some of these areas are the areas that we would attempt to mitigate using beamforming. So next we use 2 techniques that are common for massive MIMO or FD-MIMO beamforming. There are other techniques, but these represent some of the limits in 2 different directions of beamforming. The first, zero forcing, attempts to minimize the amount of interference that the beam forms to other users, while maximizing the signal strength to an intended UE. The second, maximum ratio transmission, simply tries to form the strongest beam that it can to one of the intended devices without any concern for how much this may cause interference to other devices. This second technique causes a great deal of interference and is not the best way to form the beams for multi-user MIMO or MU-MIMO, but it works quite well if there's only a single user. In our study, we used simulations. We used Wireless InSite MIMO capability to calculate the propagation and generate what's called a complex H matrix for all of the channels between the large MIMO arrays and the users within the scenes. We then used prototype algorithms that are in development for future versions of Wireless InSite to calculate the beamforming weights, the signal to interference plus noise for MIMO streams, and the MIMO throughput. Our first case was a single user MIMO case where we simply used our beamforming using the maximum ratio transmission technique to try to generate the maximum beam that we could to any point in our grid throughout the 3 cells. We then used a simple technique to estimate interference, adjacent channel interference from the other base stations, assuming that they're not directing beams to any given place at the same time, but that they still generate interference from each of their transmitting antennas. This technique clearly increases the throughput dramatically and the signal interference plus noise. In this slide we show a side-by-side comparison showing on the left the throughput that we achieved for our baseline SISO system where we simply use sector horns, and on the right we can see the throughput that we were able to achieve when we maximized with beamforming, assuming a single user at any one of the points in this grid. There's clearly a significant increase in the throughput overall. There are still some areas where the throughput drops because of the shadowing and where there are perhaps complete dropouts in areas that are well beyond line of sight. And some of this is to be expected in mmWave systems. We then put a route through many of these different regions, including some of the line of sight regions, some of the shadowed regions, and some of the areas where there's interference between base stations so that we can take a closer look. Here we show the throughput along the route that we showed on the previous slide, and we can see that the single user MIMO technique compared to the SISO baseline in blue, that we've been able to significantly increase the throughput, and over much of the route it's achieving its max 256 QAM throughput of just under 500 megabits per second. The dropouts have also been suppressed, and in the lowest regions, the worst dropout in this single user MIMO case is 142 megabits per second. Next, we looked at multi-user MIMO, and this is more likely the case that's going to be seen when we start going to FD-MIMO systems. To simulate multi-user MIMO, we placed 8 individual UEs within each of the areas around the 3 base stations. We continued to keep our route moving through the pattern along the route that we described in the last slide. This time we used a beamforming technique called zero forcing to form beams to each of these users simultaneously while trying to, with each of those beams, form nulls to the other users. So in these cases, each of these base stations was forming 8 to 9 beams simultaneously and trying to form those beams such that they would form nulls simultaneously to the other 7 or 8 users within each cell. Our assumption in these simulations was that each of the base stations received pilots from the UEs and was able to determine perfect channel state information. So this next round of simulations was an ideal case. We then calculated signal interference plus noise and throughput to each of the users in the cells. And we assumed a basic level of coordinated multipoint between the base stations, simply assuming that the base stations would not ever beamform to the user moving along the route at the same time, and would instead zero force when another base station was forming the beam. For multi-user MIMO, the signal to interference plus noise has a couple of other aspects to it. Signal to interference plus noise is a standard metric for determining the quality of the signal, and typically this includes both ambient RF noise and interference from other base stations. For multi-user MIMO, we also have to take into account the interference from beams to other UEs. So if a base station is forming a beam to one device while also forming a beam to the other device, any amount of the beam that gets to an unattended device becomes additional interference, interbeam interference. So when we applied the multi-user MIMO techniques to the same route, we then performed the calculations again, and the results of the multi-user MIMO zero forcing are shown in green. When we compare to the original baseline, there is definitely some significant improvement along the route, going from blue to green, and we again are able to achieve the maximum throughput in many more places along the route. However, we do still suffer some dropouts at several different points. And you can see that overall our mean throughput has gone from 269 up to 377 megabits per second on average, but that we do have some areas where there are complete dropouts along this route. It's important to note, however, that with multi-user MIMO, one of the things that the system is trying to achieve is not just to increase the throughput to one user, but to transmit to multiple users at the same time in that band. So when we consider this, the total peak throughput when considering all of the devices in the 3 cells has actually increased to more than to somewhere between 2,700 and 3,600, depending on which base station we evaluate. And as we have our one mobile device moving between the cells, we see some shifts in the throughput depending on where that device is. This is giving us the overall throughput that the base station is able to achieve by transmitting simultaneously to different users. This does represent the overall total peak throughput, and it does not take into account the fact that with time division duplexing, some of this throughput would have to be used for a split between uplink and downlink. And it also should be noted that most of the UEs in our example were in or near the line of sight. So clearly in places where there are large dropouts and shadows, we would have to fall back on a macro cell to provide coverage for the entire area. Next, we looked at diffuse scattering, and as we mentioned earlier, diffuse scattering impacts the propagation in a couple of different ways. First, it scatters waves in different directions than traditional propagation and reflections would scatter. And second, it depolarizes the signal. So when when we're looking at multiple antennas and perhaps trying to transmit multiple beams, there's a chance that there's some cross-polarization terms between the different antennas that could have either a beneficial or a negative effect on the propagation and the beamforming. So we refined our simulations to include these effects, and we show these in the magenta line. Overall, there definitely are some significant effects, both positive and negative, in different points along the route. And in the future, we may look a little closer to see some of the specific effects and see how these affect the multipath. Next, we looked at coordinated multipoint, looking specifically at joint transmission to see if this might be able to assist, particularly near the cell edges where we still are suffering the dropouts along our mobile route. So in this case, we looked at the cell edges, and in those locations we modified the beamforming from the zero forcing algorithms to attempt to have two base stations transmitting along the cell edges between them at any given time at the same time to a device. This essentially doubled the number of transmitting antennas for that portion of the route, allowing for 256 transmitting antennas to beamform to that device. Our goal was to determine how much JT coordinated multipoint might be able to improve along these cell edges. And we can see the effect, the green multi-user MIMO case before, to the light blue when we included the coordinated multipoint techniques. As we can see, there's some minor improvements. Overall, the mean throughput didn't change much. It only increased from about 377 to 391. Most of this, though, was due simply to the fact that in some of those cell edges where the throughput was very low, we were able to at least achieve a modest level of throughput so that our dropout areas were now at a minimum of 29 megabits per second. So there's some minor improvement, particularly along the cell edges. So next, we wanted to discuss a little bit some of the real-world challenges that beamforming faces when trying to get good channel state information for beamforming techniques like FD-MIMO. There are three limiting factors for FD-MIMO, also known as massive MIMO, in its ability to obtain the channel state information that it needs to form good beams. The first is channel reciprocity. While physics states that channels are reciprocal, the uplink and downlink transmitter and receiver chains are not. And most of the adaptive beamforming techniques, such as the one that we present today, use pilots that are coming in the uplink to then determine how to form beams in the downlink. So this channel reciprocity becomes extremely important to deal with. A second is pilot contamination. Using the technique that we just described, UEs will send pilots to a base station, which it then uses to characterize that channel for the downlink transmission. However, pilots from UEs are not always orthogonal to each other, or in other words, they're not always unique. And if multiple pilots from neighboring cells are transmitting with the same pilot signal, that can cause contamination that interferes with good channel state information. And the third is what's known as the orthogonality of channel responses. MIMO in particular relies on the channel responses from the base station antennas to different terminals being sufficiently different that it can apply MIMO techniques to improve the channel or to do things like beamforming. So starting with channel reciprocity, as we stated before, according to physics, propagation channels are reciprocal, but the transmitting and receiving chains on the uplink and downlink are not the same, and this hampers this reciprocity assumption. It introduces random amplitude and phase variations that can degrade the CSI, and when the CSI is degraded, these can degrade the beamforming accuracy and significantly reduce the signal interference plus noise and the throughput. Fortunately, this doesn't appear to be a showstopper. The technical literature includes many different research papers that have shown some successful calibration methods, and some of these methods appear to be possible to use with a minimal impact to the throughput. So it seems that there are ways to overcome the channel reciprocity. REMCOM plans to determine approaches that we can use to account for these impacts in our simulations, both from the effect of the lack of reciprocity and from the attempt of mitigation techniques to mitigate it. Next, we have pilot contamination. MIMO systems use pilot sequences from each UE to estimate the channel. There's a maximum number of unique pilots that's limited by the coherence interval and the RMS delay spread within any cell. When there are many UEs in close proximity in small cells, it's possible to exceed the possible number of pilots. When this happens, multiple UEs can be transmitting the same pilot sequence as another UE in a neighboring cell. And as shown in the diagram below, when one UE transmits a pilot and another one sends an interfering pilot, this contamination can cause the pilot to degrade the channel state information from the base station, and this can seriously affect the beamforming. Although this is serious, there is active R&D into mitigation methods, and there are techniques being researched. In our last MIMO beamforming webinar, we simulated the effect of pilot contamination, and future work could also include trying to simulate some of the mitigation techniques that are being developed to deal with it. Last, we have the orthogonality of channel responses. MIMO relies on channel responses having sufficient diversity that different techniques can be used to improve the signal, whether it's beamforming, diversity, or any other spatial multiplexing kinds of techniques. There are two traditional methods that are used to characterize a channel. They're called the rank, which equates to the number of potential streams that can be formed, and the condition number, a ratio that characterizes the ability to multiplex over multiple streams. Research suggests that with at least 10 times as many antennas as users, the channel conditions are reasonably favorable that the MIMO techniques can be successful. So this particular one doesn't appear to be an issue for the planned deployments of 5G FD-MIMO, which are planning to include large numbers of antennas and supporting perhaps 8 or 10 users at a time. Regardless, ray tracing simulations capture all these effects by their very nature, and so any conditions where this is a concern can be captured by doing ray tracing simulations. So in conclusion, millimeter wave bands bring many new opportunities for 5G. But when we combine these with the MIMO technologies, they also add significant complexity to planning and channel modeling. In this webinar, we've demonstrated how Wireless InSite MIMO and the capabilities that we're developing for beamforming and other MIMO techniques can be used to predict performance of 5G millimeter wave systems in an urban setting. We included a brief review of some of the key challenges for 5G and FD-MIMO. We've simulated most of these effects, and we're working to incorporate the rest as issues and new technologies for 5G continue to emerge. Our study demonstrates how complex predictive simulations may have to become as we approach 5G technologies. And our efforts will continue to work to address this need with our products, and we always appreciate any feedback on requirements and objectives from the wireless community. And now we'd like to take a moment to answer questions that have been asked during the presentation. One question, is it possible to define individual antenna patterns for antenna elements in an array using the MIMO capability in Wireless InSite? And it is. You can provide an individual antenna pattern for any element of the array, and you can use simulations or measurements to include unique patterns for each of the different elements to account for interference and mutual coupling between elements of a large array. Another question, is it possible to import STL-based models into the simulation environment? It is possible. STL is one of the supported inputs, and it is possible to import STL urban data to model buildings and structures. Is there a way to automate mobile placement in Wireless InSite was another question. Wireless InSite includes many different types of transmitting and receiving sets, and so yes, it is possible to define sets using a trajectory or using a route to define a mobile device moving throughout a cell. And we showed one such example in this demonstration with one of our routes acting as a mobile device, mobile route moving through the cell. Another question, does our model only support outdoor environments, or can it handle indoor Wi-Fi as well? Wireless InSite does support both outdoor and indoor, and it can do both urban and rural settings over rough terrain. There's a question about the beamforming techniques. We use maximum ratio transmission and zero forcing and other beamforming techniques. We chose to use MRT and ZF because they represent two ends of the spectrum, either maximizing the power to each device or minimizing interference to other devices. And when looking at the reverse, MRT is also equivalent to another technique called maximum ratio combining for the uplink. But there are other beamforming techniques such as minimum mean square error, and there are certainly many other MIMO techniques as well. So these were just intended as a sample of different potential possibilities. There's a question about whether there's a way to automate beam switching or beamforming in Wireless InSite. We have techniques right now. The capabilities that we showed here for beamforming, as an example, beamforming to the mobile device as it's moving through the cell, while also beamforming to 8 other devices. These are prototypes of capabilities that are in development for a future version of Wireless InSite. Those aren't available yet. At the moment, our main output from the MIMO capability is the H matrix, but once the beamforming capabilities are available, the intention will be to release those within Wireless InSite. And there's a question about the output data formats. All of our examples showed plots, and they showed visualization of fields within the scene in coverage areas. And there's a question of whether it's also possible to get file outputs. The Wireless InSite capability and the MIMO capability have different ways of getting ASCII outputs out. One of the common ones is to generate CSV files. And so it is possible to generate H matrices, receive power, and a variety of other outputs in text formats that can be used for post-processing in other ways. I would like to thank everybody for attending our webinar today. At this point, we're going to go ahead and wrap up the webinar. There are additional questions coming in, and we will do our best to respond to those questions offline in a fairly immediate. And please, if you have any questions after the webinar is over, please feel free to call the number that's on the screen or to contact sales or technical support. Thank you for attending today.